My name is Vitalii Mocharskyi and I'm very happy to represent you our research modeling the distribution of laser energy in the pulse by the photoemulsion method, which was done in Ternopil Ivan Puluy National Technical University. As you know, irradiation of materials with a high-power laser can change the structure and properties of the material and obtain various structures on its surface. Some of the structures that we received in our experiment you can see on the slide now. So energy and its distribution over the radiation spot have an important influence here. Modern methods of energy measurement are based on the use of different types of sensors: pyroelectric, thermopile or photodiode. Some of the sensors you can see on your screen. All these devices are complex and expensive. For the neodymium glass lasers that we use in our experiments, a simple and reliable colorimetric method of energy measurement is quite often used. It allows to determine the energy in the pulse, but does not give its distribution. In this work, we propose a new simple and very cheap method for determining energy distribution and its visualization, which is based on our proposed matrix model, which was implemented using the MATLAB. As an example, we used an image of an unfocused laser spot on the surface of black-white photo paper. You can see the image on the slide. The laser worked in the free generation mode. The output data for the model is the total energy which falls on the entire spot, obtained by the colorimetric method. We converted the obtained color image into gray with a color gradation from 0 to 255. We also set the condition that the black color is the area that was not exposed to the laser, the original color of the photoemulsion, and the white color is the area that received the maximum amount of energy, the color of substrate of the photopaper. Then, we determine how many pixels of the corresponding shades of gray are represented in the resulting image and presented this in the form of graph. The resulting graph shows that we have two peaks. It was empirically determined that pixels with a shade from 0 to 55 can be considered as not affected by laser radiation. Then we made all pixels less than or equal to 55 shades of gray equal to 0. Preserve linearity of the initial condition, we subtract 55 from all elements that are greater than or equal to 56. We obtained a new graph of the dependence of the number of pixels on the shade of gray. After that, we got the image already in changed shades of gray, and as you can see, it became darker. After that, we multiply the shade by the number of pixels of this shade and find the sum of the resulting array. The sum will be the energy per spot in the relative units. Then we converted the relative units into real ones. We remember that we are given the initial value of the total real energy of the laser spot, 5 joules in our experiment. We divided the real energy by the entire sum of the relative energies and then multiply by the hue element. We replace the numbers of the shades of gray with real energy values and get graph, which you can see on the slide. So after that, we can easily build a three-dimensional graph that will show us the real energy distribution over the spot. It should be noted that the proposed model also allows determining the type of transverse modes with axial symmetry in the laser pulse. The first number means the number of intensity minima along the radius of the cross-section. The second is equal to half the number of intensity minima in the azimuthal direction. Now about the conclusions. The proposed model allows determining the distribution of laser energy in the spot by the photoemulsion method. This can help to improve the processing technique more accurately selects the parameters of laser irradiation and also facilitates the explanation of the obtained phenomena. So thank you for your attention, and if you have some questions, you can contact me using email that you can see on your screen.